Spring convention, our 20-year convention, our 20-year anniversary. So this year, by the way, I'm Rick Edelson, for those that don't know me. I am the former chair of the Technical Activities Committee. I'm now retired as the technical chair. So because I'm retired, they get me to do other things. So they won't let me go. Today we have a good set of presentations, and also tomorrow and Friday. Today we're doing a half day, so you all are going to be free this afternoon. Anybody out for golf, swimming, spa, you name it, you can do it. So you'll be able to enjoy yourself this afternoon. This morning we have a set of presentations for condition assessment. We're going to talk about condition assessment, how it used to be and how it is today. We have a set of three presenters, although the book says four. Matt Sherman unfortunately wasn't able to make it, so we're going to be with three presenters. And first we're going to start with Peter Kolf. Peter is with CTL, Senior Principal Engineer. Did I get that right? Principal Engineer, Senior Principal Engineer. No, Principal Senior Engineer. He's one of the best. Okay, we'll just stick with that. He's been at CTL since 1987, the year before ICRI started. And I know Peter for many years. We're definitely great colleagues in the industry. So let's start with Peter, and we'll take it away.
Well, we're going to begin, I think appropriately enough, with a look at condition evaluation, since that is the first step in the whole repair process. I'm going to give, I think, kind of a general overview, and I'm going to look at some of the standard development that's occurred over the years. Larry will be speaking to the advancements in NDE, and Tanya will be talking about developing university education programs. ICRI's purpose: to improve the quality of concrete restoration, repair, and protection. It certainly can be argued, but since I've got the floor, I'll say that I think that the most direct way of improving the quality of concrete restoration is to improve the quality of the evaluation. If you don't know what you have up front, your repair is doomed. So the evaluation itself, obviously identifying the cause and extent of distress or deterioration. There are going to be projects where the causes are very apparent. Obviously here we have congested reinforcing steel that led to all sorts of problems. But even in a situation where the causation is apparent, a condition evaluation is still necessary to understand the full extent of the problem prior to entering a repair program. Again, obvious cause: this is a fire damaged structure, and this is the same facility also damaged by the fire. But again, although the causation is obvious, quite a bit of work needed to be done to define the limits of the deterioration here prior to developing a repair program. So let's look at the process, the evaluation process, and I've kind of outlined it here. You know, you could throw other things in here, but just broad brush. You obviously have to begin with a knowledge base and an experience base. There's your basic document review. You have to find out as much about the structure as you can before entering into the evaluation. You need to get your hands on the field inspection, see what the conditions are, identify the nature of the distress, identify how widespread it is. Typically, well, oftentimes, you'll be taking samples for laboratory testing. Some projects will go into another phase of structural analysis, and then obviously at the end you've got to summarize your work and come to your overall conclusions. We're looking at evaluation then and now. Obviously, some components are the same then and now. Obviously, the document review and the summary analysis, there is no change in that, except that these days we tend to have more to synthesize at the end because we can obtain more with some of the developments, particularly in NDT. I'd like to look for a moment at kind of the evolution of our knowledge base. I found it kind of interesting putting this presentation together. As a structural engineer, when I'm looking at a structure, I can generally find design standards that go back to the beginning of the 20th century. But the evaluation process is not that way at all. And like I said, in preparing this, I found it pretty interesting. Hope you do as well. Tried to get back, I think I found something about the roots of when concrete deterioration began, but obviously I wasn't finding much in the way of evaluation standards for quite a while. We get into recent history. 1957, ACI Committee 201 was formed. So, you know, I'll say at this late date, concrete's obviously been around a while. We're finally getting a committee formed to address specifically durability of concrete. 1962, they come out with an ACI journal publication, which is addressing durability. Again, something far short of an evaluation standard, but certainly the first steps of the process. 1968, they come out with another standard guide for making a condition survey. This is, it's a brief document. It's 14 pages, a lot of photos, just kind of saying if you see this, you might have this type of thing. So it's not exactly an in-depth condition evaluation standard, but it's certainly a good first step. 1975, again, from ACI 201, we've got durability of concrete. 1976, there's a great publication, Testing Hardened Concrete Non-Destructive Methods. So this is an NDT document, but this NDT, this document is really addressing concrete quality, concrete strength. It's not talking about flaw detection, or for the most part anyway. We're talking about ultrasonic pulse velocity, Schmidt hammer, Windsor probe, correlations between some non-destructive test methods and concrete quality. 77, again from ACI 201, Guide to Durable Concrete, has something on evaluation and repair, but again, it's pretty brief. A third of a page on evaluation, a page and a half on repair. 224.1, causes evaluation repair of cracks in concrete structures. Again, we're developing the basis here. We still don't have an evaluation standard. 1986, I think, is really what I would call the first kind of comprehensive evaluation standard that we've got. This is just immediately prior to the formation of ICRI. The only problem with this document, if you call it a problem, is that it really is geared toward Corps of Engineers structures. So we're talking dams, locks, pavements, that sort of thing. So, the big day, ICRI is formed in 1988. Documents formed shortly thereafter, well, within the next 10 years, I think, really form the basis of the current standards that we have for evaluation. Not so much the first 228.1 because it's specifically geared toward estimation of concrete strength. Useful, but not really the evaluation process per se. But the next three standards are very much directed at, you know, they are the standards in large part for a modern condition assessment. ICRI has developed some of its own standards, and I think, you know, consistent with the philosophy of ICRI, it's not trying to redo good work that's been done by others, you know, that these documents that we've already seen, but it is it's looking at key problems within the industry and trying to take a focused attack, if you will, at needs of the industry. Concrete Repair Manual, obviously a really broad document to just try and put all the information in front of you, give you a resource that you can pretty much find anything in. The Guideline for Evaluation of Unbonded Post-Tension Concrete Structures, again a focused document specifically for post-tension concrete structures and a very needed document. the guideline to bond pull-off testing, a key document, one that, you know, ACI took a crack at, ASTM was taking cracks at, ICRI beat them all to it. We have an upcoming evaluation document, and I'll give just a brief summary, entitled something like Non-Destructive Evaluation Methods for Condition Assessment, Repair, and Performance Monitoring of Concrete Structures. There have been so many developments in NDT, particularly over the past 20 years, as Larry will be addressing, that we felt that a brief guide was appropriate to just essentially, as I've written here, guide someone through the maze of the various NDE methods. These are the basic chapters, obviously purpose, scope, chapter on just a very broad discussion of NDE programs. And the next 3 chapters are geared toward condition assessment, repair program, quality assurance, quality control, and then performance monitoring with NDE. And the real meat of the document is the guideline tables themselves, which cross-reference methods against applications. There's a pretty extensive appendix if you want to get further into the specifics of a given NDE method, and then there's an appendix with just a lot of references regarding evaluation. I don't expect you to read this, but this is one of the tables. There are 4 primary tables. This one is specifically focused at strength prediction. We have the methods across the top. We have the various ASTM or other standards that apply to the method. We have the applications across the left. Across the bottom, we've got the references to the appendix where you'll find more information on the test method. And then obviously just, you know, a series of X's to cross-reference applications versus methods. Another table on just general condition assessment, another table directed at foundations, and a final table which is directed toward reinforcing steel, in particular, that is, you know, locating reinforcing steel, finding depth of reinforcing steel, identifying corrosion, half-cell potentials, corrosion rates, that sort of thing. So the next steps, this is, I think, what Vision 2020 has been looking at now for a few years. Obviously, we need to continue to improve our standards. We need to continue to research issues that we have room to grow on. And we need to be developing formal education programs, I think, to bring up the new crop of people who can move things forward, and that specifically will be what Tanya's discussing. Back to the process, briefly, laboratory testing then and now. The basic tools are the same 20 years ago and today. Petrographic examination, chemical analysis, physical testing. Like I say, these are pretty much the same then and now. The difference, I would say, is that we are capable of more now. 20 years ago, we didn't have an electron microscope. Now we do. So for high-end analyses, we have tools available today that we didn't back then. I would also say that, in general, petrographic examination is getting more complicated because whereas 20 years ago, we were generally dealing with what I'll call vanilla concretes, basic, you know, Portland cement, aggregate, that sort of thing. Today, we have specialty concretes that have all sorts of pozzolans, all sorts of admixtures, and you can get into chemical compatibility issues in a heartbeat. And a lot of that is hard to diagnose strictly with a petrographic examination. So that could lead to the desire for further chemical analysis, and like I say, some of the more high-end stuff. Structural analysis, yesterday and today. Obviously, today we have analysis tools that we didn't 20 years ago. On most projects, this really doesn't come into play, but certainly, like I say, for the high-end projects, the specialty projects, to have these types of analytical tools at our fingertips is useful. Back to the process, field inspection and condition survey. the basic tools are the same. The basic condition survey tools. Obviously, you need to start with knowledge and experience, visual inspection, hammer sounding, crack mapping. Same 20 years ago and today, and it'll be the same 20 years from now. Oftentimes, inspection openings and sample removal, even if you're doing a lot of NDT, sample removal is critical for verification and calibration of the NDT. And then, of course, we get to NDT, where significant advancements have been made in the past 20 years, and that'll be what Larry is addressing. But before I hand it off, I have a couple archival images. This is bond pull-off test equipment from probably about 20 years ago. This is what we would have done. This is really, a lab test done in the field. It's all lab equipment assembled in the lab. We've got a hydraulic ram with a load cell, and we've got the load cell tied into data analyzers. And so, you've got a hydraulic ram, or rather a piston off the background where, we can pump the hydraulics for the pump. So just doing a bond pull-off was an endeavor. Another archival image. This is a radar 20 years ago, a beast, and it produced only hard copy. You had the hard copy image from the field, and that was it. You lose it, all your data's gone. And I guess brownie points for the person who can pick out the TAC member in this photo. And with that, I will hand it off to Tanya.
Thank you, Peter. Do you have your presentation up? Okay, while Tanya's bringing up her presentation, let me introduce Dr. Tanya Wattenberg. She holds a PhD in architecture from Texas A&M, historic preservation from Columbia, MS in historic preservation from Columbia University in New York, BS in landscape architecture from University of California, Davis, and a certificate of historic preservation from Texas A&M. He's currently on the faculty of the Concrete Industry Management Program, a new program, at CSU in Chico, and is a corresponding fellow of the Center of Heritage Conservation, College of Architecture, Texas A&M. She has extensive experience in building design and preservation, and directs academic and professional research in concrete repair and preservation. She has developed computer graphic methodologies for many areas of building professions, and she's joined us a couple of years ago and brought her program to ICRI so that we're all now learning about it. And it's a great idea, and it brings a lot of education to an area of ICRI that we never had. So let me introduce Tanya.
Thank you. All right, well, I have the pleasure of having some very fun slides to use to demonstrate the things I'm going to talk about. I'm going to address condition assessment from the academic standpoint, what we're doing in the universities. And one thing I'd like for you to keep in mind as I'm talking is how any of this might affect your companies directly, in terms of interns, future employees, that type of thing, because I think we've come a long way in the academic part of this. And particularly at our school, we have a big focus in repair. We teach a required full semester lab course in concrete repair. So you'll see a lot of images of what our students are doing. And this is a quick background. The CIM program is Concrete Industry Management. There are 4 universities across the country. Potentially one more will be joining us in Texas. The other existing programs are in Tennessee, Middle Tennessee State University, New Jersey Institute of Technology, Arizona State, and then California State University, Chico. And eventually there may be one in the Midwest as well. So the potential for employees, interns, collaborative research, everything. It was designed to kind of cross the country with the different universities. So keep that in mind as with the things that I'm talking to you about, and any specific questions you might have about that, I'd be happy to talk to you about. So the first thing I'm going to talk about, there's a few main points I want to bring up, which is the kind of the then and now, because that's the theme of the conference. Some things that I see for the future of academia, where we're going, especially as it pertains to specifically repair, not just concrete education, is that one thing is that I've heard from some other universities is the idea of internationalization, getting students and programs involved in projects all over the world, not just in our hometowns or in our own labs. And there's a lot of opportunities developing among universities and with professionals, both at home and internationally. And that leads kind of right into the idea of how we're teaching more these days. Any of you come from construction management programs? Okay. We're often confused with construction management. We are a completely different program. We're a standalone Bachelor of Science degree in concrete industry management with a required minor in business. So, and one thing where I think where we're differentiating is that we have a lot of hands-on we have a lot of lab courses that are required, and that's part of the goal of this whole concrete program, is that we not grow to the point where we can no longer hold lab classes because we have too many students, which is something that a lot of the concrete or the construction management programs are dealing with in the academic environment right now. You get too big and you can't go on field trips anymore. You know, it's one thing, you know, and how can you teach construction or concrete without going on a field trip? You know, honestly, it's an issue. You know, when you have 20 students in a class, you can rent a van and you go on a field trip. What happens when you have 120 in 3 different sections that meet at 5 different times of the week? Logistics of going on a field trip. It gets kind of crazy, but that's one thing that we are sort of chartered to do with this program, is keep the hands-on part of it, both in the lab and in the field. Another thing that I see coming on even more, especially with the whole non-destructive testing becoming so big in the industry, is that it leads to multidisciplinary projects for students and professionals. One thing, and I'll show you some images of a research project we just have been working on in France, and that included students from Texas A&M. It was really a Texas A&M based project that we got to get involved in, but it involved geophysics people, survey crews, architecture students, and engineers, and then the concrete students as well. So the multidisciplinary aspect of what students, I think, these days are getting involved in is I think, a really great thing. And then the last point, and I'll get to the slides in a minute, the last point is that there's so much now with repair that there's a recognition that full courses like we're doing at Chico are needed. The program in Arizona, many of you may know Luke Snell from Arizona State University. They will be bringing on a full course in repair with their CIM program. Tennessee wants to do the same thing, and with what I've been able to do at Chico this semester, with a lot of support from ICRI and people right in this room, we are kind of developing the prototype course that the other CIM programs will be offering as far as a detailed lab manual, and we're always open to guest speakers and suggestions for lab projects and that type of thing. So I think that idea that there will be more full semester long lab-based courses in repair, I would say in the next, I'm going to guess, 3 or 4 years, at least 3 of the 4 CIM schools will have a full semester lab-based course. Okay, this is one of our gals drilling a core sample, and this is what I was talking about as far as the hands-on thing. Here, and some of them chose some interesting materials to put into their samples, but here the students are creating full-scale, or scaled mock-ups of a sample of concrete that was meant to have, I told them, be creative, and some of them got very creative, as you can see. Create voids, I want things in there, and one of this project was to have the students build forms, put some objects in there, and then you can see there's a grid on the bottom of the plywood. They had a separate piece of paper where they gridded it off as well, and so they mapped the objects they put in on a separate piece of paper, and then in a couple of weeks, let me go to the next one. Here, went ahead and filled them up with concrete. We're going to switch samples among the teams, and then a different team has to try to find those objects through non-destructive testing methods in somebody else's sample. And we'll see how well they do. I'll let you know next semester. Here's another hands-on exercise. Let's go to more. This one, they built styrofoam mock-ups to, one of our guest speakers got a hold of me ahead of time and had the students build 2x4 panels out of styrofoam with some rebar in it, and then a simulated spall, complete with the ICRA profile chips. They had to kind of try to get the styrofoam to the right profile. That was interesting, because in a lab where it's a big lab, a lot of air blowing around, and little styrofoam balls all over the university. So I learned from that one. We'll do that one differently next time. But this is hands-on work. Here they're outside playing with some equipment, and we have another lab coming up in a few weeks that one of the companies in our area is going to come in and bring all kinds of equipment and let them work with it. This is the sort of the case study that will illustrate some of these points. We were very fortunate to get to work on this project. It is Pointe du Hoc, which is the D-Day landing site at Normandy. This is where the Rangers of the 2nd Ranger Battalion came in prior to the major invasion force, and there's a lot of details that we could talk all day about. They climbed the cliff and had to take out the guns that were capable of firing on Utah and Omaha beaches. And this is a very important historic site, and there are a lot of problems with the concrete. You can see the vertical element right there on the top of the cliff is the monument to the Rangers. We all know the history of what happened and the numbers of servicemen who didn't come home. The monument at Pointe du Hoc sits on a forward observation post that is no longer accessible to the public because it's unsafe. The rest of the site is, but the American Battle Monuments Commission, who has jurisdiction over this site, has a priority from our federal government, working with the French government, to get this observation post open so that people can get out and see the monument. So we were brought in because of the concrete part of it. Believe it or not, their initial project did not include looking at the concrete. They were concerned about the stability of the cliff and doing a detailed site survey. Several years into their project, they decided that the bunkers and the concrete needed attention, and so we were fortunate to get to do that. I took 5 students over spring break last month, and we conducted a lot of the tests, and Larry's going to talk in a minute, but Larry was wonderful and accompanied us and brought his equipment and trained the students on site, and it was just a phenomenal experience for everybody. Just to give you some idea, if you see way down at the bottom of the slide, there's a little bit of a blue jacket. I don't know if it's clear enough where you can see it. See, there's a little white element sort of right in the middle at the bottom of that pile of rocks. That's a person. Now, this is the cliff that the Rangers had to climb under fire, and this is a Texas A&M student who got stuck down there and spent better part of the day trying to get out. They had to send their climbing expert down to get him, and the only other way out was to wait 45 minutes for the tide to go out, and you have to hike 45 minutes down the beach and come up around the other side. So he could have gotten out. We didn't have to call in the Coast Guard or anything, but so this was our first day. But it gives you some idea of the scale of what those Rangers had to do and why preserving a site where they succeeded in their mission is so critical. And you can see down at the bottom, just off to the left of the slide, there's a little cavern at the base of the cliff. That's the issue right now, is the cliff is falling out underneath the site. And what they figured out is that because of bombing on the entire cliff edge on D-Day, it fractured the limestone so badly that that's actually caused by groundwater from behind, not the force of the ocean hitting the cliff. And so one of their solutions is they're going to go, and it's a temporary fix, but they're planning, believe it or not, to go shotcrete these caverns. And they're going to drill piles all over the site, try to stabilize it at least as a temporary fix so that they can get that forward observation post open. This is a view just to the left, and to give you another idea of what the scale of the cliffs is like. Bomb crater. These are, okay, and this is, first day right off, students are learning about, initial visual inspection. The first thing you do is walk around, see what's there. That's Larry in the dark jacket. Here's another one. Walking around this site, and I can't take credit for discovering this, but this is a keen eye for visual inspection. Anybody know what that is? It's a bag of cement. Yeah, there's a whole pile of this cement that was left there. There was a new structure being built on D-Day that was only half complete. I think I have a picture of, no, I didn't put it in. What happened, the construction was was done over 2 phases, prior to the war and after the war, and during the time of D-Day. So we were fortunate to have samples of cement, and actually CTL offered some time for lab testing from the samples from this site 2 years ago. So we have a lot of people involved in this over time. Here's 2 of the students beginning to do the tests down in the observation post. And again, this is the structure that's no longer accessible. So these students we learned about this in the class. We're using Peter Emmons' book and some others in the ICRI repair manual, the big reference manual. So they've learned about this stuff in the classroom, talked about it, what all the different tests were, and then they were able to learn it and apply it over a week-long project in the field. And I should point out that as you're doing a test like this, you might look up and find a bat. So it was interesting. This is the only structure that had electricity inside, so finding the bat in the dark was also kind of interesting. Here, one of the main reasons we were there was the A&M team needed to find foundation depths. They're going to be driving these piles, and they wanted to know how deep the foundations went. We have historic documents about how a typical German bunker should have been built. We don't know for sure if they actually built them that way. They are actually amazingly accurate all up and down the Atlantic seaboard. They were built German style, right, as they should have been. But one thing we found is that, oddly enough, there was an overlay on the floor of a lot of these bunkers. Not sure why. We found some patches where the overlay it was pretty much debonded all over, so we had a hard time getting these depths, but then discovered a few patches where we could work right through that. So this is just, great stuff for students. Why, trying to get a depth and why isn't it working? Well, tap, tap, tap. And here's outside the observation post. If any of you saw The Longest Day, that movie, they show the observation post in that one. So this is part of it. This is a walkway around the front where they needed to know the depths of the concrete. These gals are locating rebar. Also talked about the importance of calibration and figuring, these are the real world things that you don't necessarily worry about so much in a lab. It's easy in a lab setting with students to say, well, in a real case we would do this and that, but we're going to fake it in the lab. This doesn't let you do that. Also, the importance of, it's sort of like an architect who draws perfect drawings on AutoCAD. Well, we all know that things don't really get built that way, right? AutoCAD, everything's perfect in 90 degrees. Well, it's not that way in the real world. Well, when you've got a wall that was bombarded with a shrapnel grenade, and there's not very much surface area you need a smooth surface area for contact. This was a case where, just finding a suitable area to attach the equipment was interesting. This is one of the casemates that was built at the time of D-Day. The other gun emplacements were open. These are the newer ones that were being constructed. And here are 2 of the guys. You can see the gentleman on top, and then down inside, he's holding one end of the transmitter. Robert down inside is holding the receiver. And just inside of the barbed wire there, Andrew is running the test off of the computer. And the 2 gals are in the background there getting ready to do some other tests. So, again, in the lab, it's easy. You have easy, let's see if I can find, you have easy access. Mock-ups are created for ease of doing a test. Well, in this test, you have to kind of figure out where the top person is relative to the bottom person. You can't just kind of say, well, you're about right. So, it was difficult, and we got it as close as we could, but it's a good lesson, getting those students out in the field. This is I think one of the best then and now slides. Courtney is holding a Schmidt hammer, which is something we've done in the lab for a long time in classes, not necessarily just repair classes. And then Chad is standing in the background locating rebar with something a little more sophisticated. So they're learning all aspects of it. This is the importance of, this is the last day the sun finally came out. Downloading data before you leave the site. That was something. Okay, we don't want to just walk off with the equipment and not have a second copy, so we spent some time getting everything ready. Then I have a few more images just to finish up, and then I guess we can do questions after if we need to, which is just the sheer destructive nature of what went on. This is a gun mount that was just completely blown out of its structure. Sits where it was the day it landed after D-Day. This site is completely open. Rebar, rusty, sticking up everywhere. You can climb all over everything, go down inside these dark things. It's an amazing difference in that the French government is a little more lax on, personal responsibility. If you want to climb on it, it's your risk. This is just a big block of concrete that was just blown out of its location, and it's really all about the students. It's training them for what you guys are going to need for them to be able to do. And they are just, this project more than anything made me realize these students are they're sponges. They just love to learn this stuff. Especially, they love the technology of the non-destructive testing and the equipment. But they really care, and especially when they get to do the hands-on stuff. And this is just one of the packing the equipment out on the last day. So, really, that's what I had to say, is that...
I was wondering, you said there was a rebar was in there. How corroded was the rebar? Was it able to look at it?
We were only visually. We had intended, intended to do full corrosion study. We were not able to, time, manpower, equipment, stuff like that. So that hopefully, we're hoping this project will continue in future years. There's a lot more work to be done.
You're going to use that as a kind of a historical thing?
Well, they are, should we save questions for later? Or what do you think? Okay, I think, that's all right. Larry took a quick break, so I'll talk for another minute. Right now, the issue is stabilizing the cliff. That's their major concern. And it's going to be a concrete-based solution with the piles as well as the shotcrete in the caverns below. The next phase that we're working on developing with Texas A&M would be more in-depth on evaluation of the concrete. And then, hopefully being able to suggest, there's a lot of issues because the American Battle Monuments Commission is not an agency that deals with restoring buildings. They deal with preserving monuments. And so their concern is that monument that sits on top of the observation post. This gets into bigger issues of whose responsibility is it, the French, the U.S., and we have politically we have to be careful what we say. But hopefully, we're hoping that this project will continue in future years, that we'll be able to take more students, collect more information, and it's a pretty important site for that reason. Thanks. Sir.
Thank you, Tanya. Thank you. By the way, I'd like to remind everybody, they have these green sheets, which is your condition assessment of what goes on. So if you can let ICRI know how everybody's doing, certainly please fill them out. Larry, if you can bring your presentation, put it in. Okay. While Larry's putting in his presentation, we have saved the master of non-destructive testing to the end for our condition assessment then and now. Larry Olson is the president and principal engineer of Olson Engineering and Olson Instruments, which are headquartered in Ridge, Colorado. He's nationally and internationally known for his expertise in non-destructive evaluation and structural condition assessment. Larry is the chair of ICRI's evaluation committee. And as Peter had showed, there was a slide a little bit about what we're doing, and hopefully Larry will talk about a little bit more. He's an instructor on ASC's seminar in structural condition assessment of existing structures, member of ACI Committee 228 on non-destructive testing, as well as 309 consolidation. He's over 27 years of consulting experience in condition assessment on all types of things, materials, pavement, geotechnical, geophysical, vibration, just to name a few. So let me introduce Larry Olson. As soon as we technically get up and running.
No problem.
Larry has a reputation. While he's doing that, I'm going to talk about Larry's reputation. He's always known for coming in about this far below the wire on testing. He just came in under the wire.
Oh, I could make a comment on that, but I choose not to incriminate myself. All I can say is this is a week in which I've been testing with some very interesting military gentlemen at Fort Knox, taught the Tennessee Valley Authority a class all day yesterday on ASCE, and I made it here. So, not a lot of sleep, so that's my only defense. I guess I'm too busy. All right, let's see. This would, of course, be the new Windows, isn't it? Where do I find the nice little view down thing that tells me which one to open? Does anybody know offhand? Top left? Which one? 3? There? There. That's like my window? That's not what I wanted. Well, I can probably find it down here. That's the one I want to start with. Okay. Now click this one to start it. Thank you. Okay, very good. Okay, I think I've really enjoyed the first two presentations. It was a privilege to work with those students. I'll just reiterate what Tanya said. They were a lot of fun, and they went from freshmen to seniors, so you had a whole range of experience. And they donated their spring break for mostly a lot of hard work. She didn't mention the weather. It was a gale. It was 80 miles an hour, I swear, the first day, and windy, most cold until the last that week. And but we just worked right through that, and we were grateful to be inside the cold concrete. It was a little better than outside. But amazingly enough, that slag concrete has done quite well. There is corrosion of the rebar. They didn't use much rebar. It was like 16 inches on center, maybe 3/8 of an inch bar, like an 8-millimeter bar. And so there's several things that I think you'll be reading about if we get permission to publish. Have to be careful about that, as you mentioned, in an ICR magazine article at some time. So we'll hope the Concrete Repair Bulletin, we can talk about that. So what I'm going to talk about today is trying to, in the theme of the conference, talking about non-destructive evaluation in 20 years. And I just kind of characterized it from the Schmidt hammer to imaging. And that's really sort of what has occurred in terms of advancements in technology. So as we go through this, Schmidt hammer, had one of those a long time, certainly useful. But back in 1988, I think the only other thing practically was being done much for strength was the Windsor Probe. The pins were being fired in and testing was being done. Then some developments came along. The pin penetration resistance test, firing the needle, looking at mortar, looking at concrete, checking it with that, and the correlations, of course. And it's critical in non-destructive evaluation. I thought Peter did a very good job to emphasize the destructive correlation. Because without destructive correlation, particularly in strength, you just know it's relatively hard and strong and relatively soft and weak. You don't know the strength unless you follow the ACI 228.1R guidelines on how you should calibrate your NDT method to predict strength. I know a horror story over in the Micronesian Islands of somebody who used a rebound hammer to predict strength on a big bridge. They didn't correlate it. And they ended up having a failure on the bridge when they post-tensioned it and compressed it because they didn't calibrate it to a single core. And they assumed it was 8,000 PSI strength, and I don't want to offend any manufacturers, but using that manufacturer's guide, they used that and applied it like it was real. It's not real without calibration. This just shows a correlation. Very good one on a mortar curve and a concrete curve of penetration. And you'll see in this case with the pin penetration, as the pin goes deeper, it's weaker. Makes sense, right? So that's what happens. So you've got this correlation, the ability to predict strength non-destructively. And as Peter mentioned, I thought he did a great job. In fact, I'd love to get a copy of your slides because you did that historically so well of the evolution. But he talked about this, that we weren't doing that much, but you had to have the destructive correlation. The pull-out test came along, very much like pulling out an anchor from a masonry wall. And the capo test came along a little later, where you can, and that was more like recently in the late 90s, early 2000s, when you can route out a hole and pull it out. And that would be the embedment in fresh concrete and pulling it out for quality assurance and control of strength, say you want to move the forms early, but then have the ability to route that out, embed an anchor, and pull it out in existing concrete is the capo test. And that just shows a pull-out test being done. It's really kind of a shear failure, isn't it, when you're pulling that out? But you can look at that and see that you can correlate that either to tensile strength or compressive strength. And again, it's part of the ACI 228 guidelines. Maturity meter, something that started being developed in the 80s, looking at heat of hydration over time. Dr. Nicholas Carino led the way in this area, in a lot of areas. So he did a lot of research on this, and others did too, and just plotting up time and temperature versus strength in the laboratory. So you can very accurately go to the field, do your measurements, and know, well, okay, it's 70 degrees in the laboratory. It's been 40 degrees on site. Where am I at in my strength? Can I move the forms? Things like that in quality assurance of new construction. And nowadays, this has been done with small embedded sensors that can be electronically read, basically, and left in place, instead of thermocouples and cutting off the leads. Certainly, some significant developments. Half-cell potential has been around for a while. Just simple half-cell with a voltmeter, going out there, finding the corrosion activity, mapping out areas of hotspots. Well, significant developments have occurred in the last 20 years. Two of the main instruments, G-core, I'll show now, and I'll show a galvanostatic pulse approach a little later. But this is the idea of, by, in a simple sense, projecting a current at the rebar, watching how that current behaves, determining its rate of corrosion, and estimating that if you're checking it seasonally. That is a great simplification, by the way, of the technical process. But it also does concrete resistance, and lower resistance concrete corrodes faster. Maybe it's contaminated by de-icing salts, something to make the electrical properties, the resistance drop down. You get faster corrosion, if you will, in a simple sense. So this type of instrumentation being used in the field to estimate corrosion rate when it's critical. Now, if it's so corroded that you don't need to check it, that's a different issue. If your bar is gone, your bar is gone, and you have different problems. This just shows, I thought it might be interesting to look at, and I remember this very well. On the upper left, some of you may know Dennis Sack, our Vice President and Associate Engineer, with what we used to affectionately call the Beast. When I was a young man, the Beast weighed 100 pounds in its shipping case, and it had a single floppy. It weighed 70 pounds outside of its shipping case, and in 1985, I was grateful to have that floppy, very grateful. For $25,000, grateful. This was being used in aerospace. It would take 4 channels of data and do time and frequency analysis. It was very durable. It never broke, except the cards would come out. When I'd see the airline guys taking by $25,000, which was a lot of money in 1985, and just heaving it. Whoa, I hate this thing. All the time I saw them heaving it. They just hated it. So but I give them credit for it held up, but it never really broke. I was surprised. We had to reseat the cards several times. They would vibrate out on the inside. But the reason I was grateful for that is my whole graduate research in the late 1970s at the University of Texas at Austin. I was only a master's student there. The PhD got the first one with a floppy in it from Hewlett-Packard. This is a competitor, Scientific Atlanta Spectral Dynamics System. And I had to take 2,000 Polaroid photographs of my oscilloscope screen to graduate. So I've never liked the Polaroid camera. So on the right is kind of the next step in what we started doing with instruments. Compaq Computer came out with the first portable. And I still have their first portable. I actually used it in the field. This is not that picture. This is the later generation. This had a plasma screen, but you couldn't see it so well. You had to put a screen around it, a sunscreen to make you see it. And it had, I think this was an old, and if you're too young, you won't know this, but it was a 386 processor. And that was a big deal. It was the first step up from some of the earlier ones. So that would take good data with a card inside. Then we got tired of not having batteries. And we said, okay, we're going to build the world's largest PC, and we did. Maybe not quite. Compaq was slightly bigger in their first one. But that's our first ruggedized PC we ever made, with internal batteries on the left, plug-in modules, and you could do a bunch of different tests. On the right is our current PC, and that's the one that's now up to equivalent of a Windows XP Pentium M. So it's getting smaller and lighter. That one with batteries in it's 23 pounds. So it's all getting more ruggedized. The advancements in electronics are helping us to process data much better in the field, and really to just be out there and not have to worry about your equipment so much. Always before, we always had to have generators. Doesn't sound like a big deal, but if you start dragging it around a construction site with your umbilical cord being the power cord, it's a big pain to do that. The first time, we've been lucky enough to test some pretty dams over the years, and so we've made the cover of Civil Engineering magazine twice in the course of our company. The first time was testing this thin arch concrete dam in the mountains of Colorado. It was really a very early application of impact echo testing in a consulting sense, as Dr. Nicholas Carino and then Mary Sansaloni had developed this. We implemented it early on, and we got to test that beautiful dam, which had freeze-thaw damage. It's in the mountains of Colorado at about 9,000 feet. The picture on the left is when the consultant worked on it. By the time we could get a contract, it was late November, and it was cold. The problem was freeze-thaw damage on the downstream face. They wanted to know how deep that damage was. So we decided we could do that with impact echo by testing at different points on the dam and rappelling down the face. And you can see the damage on the right. And we hired this gentleman. I still personally, my hat's off to the soldiers who tried to climb that cliff. It's not my thing. Somebody has to run the equipment, I always said. But we hired a gentleman who was trained in rappelling and gave him a hammer and a accelerometer and left that big beast of an analyzer up on top to take the data, ran our generator, and we got the data. But it took a while because some of the modern climbing techniques that they've developed now are better too. But when he got to the bottom, he literally had to walk a mile up to get back as he went down the canyon, which was okay because he about froze to death hanging there and testing as we were doing the work. One day it was -10 and snowing. It wasn't easy conditions that we did that work in. I was grateful. We've done about $2 million of research over the years, and so there's been some interest, not a huge interest, but the National Science Foundation, the Federal Highways Administration, the U.S. Bureau of Reclamation have helped us and others in grants to advance non-destructive evaluation technology. You know, it pales in our research money we get in construction in comparison to medicine, but like I say, you know, concrete doesn't complain about being cored and drilled, and it can't call its congressman. So we get a lot more research in medical, non-destructive evaluation. What we did, though, was we decided that maybe we could have a moving source, which is on the left, and a fixed receiver, and attempt to image voids in concrete. And that's what our study was about. So we did this about 1995. The work was completed. Those were little voids. We cast simulated cracks, a bunch of different types of voids, honeycomb included, in 4 different walls. We did the scanning. There you see the fixed receiver, very intense scanning every inch we were going. And on the backside, what you don't see is the source was going click, click, click every inch as it was rolled up this back of the wall. So it was through transmission, ultrasonic pulse velocity, and on the right-hand side, you can see, actually, maybe I'll use the mouse. You can see the voids. Those are the slow velocity zones. So we did image the voids, which we thought we could, that it should be a bit slower. It's not as good quality concrete. You know, it's a void or it's honeycomb. So we were imaging these flaws. So along the title of my talk, this is the first time we started to try to image things. How did we do that? Well, we worked with Dr. Al Balch at the Colorado School of Mines. He's now retired, but he was a geophysical professor who'd been doing research for detecting tunnels for the U.S. military, and he had simulated a tunnel in a big piece of concrete in his laboratory. And so we supplied our expertise with his expertise, combined it to get into tomographic imaging. This shows a typical scan on the left, and what's plotted there is basically the signal as you look at it. This is the amplitude right here. Right here is the amplitude, and here's the time. So we were looking at signal amplitude, and there's little bumps in that signal because of scanning up and down. So you had a fixed receiver, you scan 4 feet, and all those different angles are recorded and analyzed, and this is actually the anomaly right there in that particular scan. And then that helped produce many scans at many angles, produced the image on the right. But it didn't take so long because it was a rolling source with a fixed receiver. We just go zip, we had a little rig with a wire and a cable and pulled it up quickly and did it again. The early cross-hole sonic logging, which is actually the first technical thing for quality assurance of drilled shaft foundations, that we use tomography on to image defects. And we still do that routinely today when people want to see the size of defects. I threw this picture in so you could see I was once a less substantial person. I thought it was interesting when I saw this. It said, oh, that's why you used to play basketball when you were younger. You didn't have as much weight to lift off the floor. So in any case, that's a big 12-pound impulse hammer. That's one of the interesting developments. It's actually a $2,000 hammer with a force transducer in it that helped advance foundation testing, to being able to look at it in a transfer function, vibration, modal testing type analysis. And this was research sponsored by the Association of Drilled Shaft Contractors on defects. This testing, both the echo testing, but in particular the cross-hole sonic logging, has gone on to be used by almost all of our DOTs for quality assurance of underwater concrete placement in big drilled shafts at bridges. So it's commonly specified. There's an ASTM standard. That's another thing we didn't always touch on. These tests are finally becoming more and more standardized. And that's still a lack. We need the non-destructive evaluation methods that are mentioned by ACI are still not all in ASTM. So it's something I think I'm going to encourage people to join that committee and push it forward further. Those were supposed to be hidden. Ultrasonic pulse velocity. This also, I think Peter mentioned it, has been around a while. It started actually as part of some, I think, war research over in Britain, if I'm not mistaken, and also a Canadian researcher. They wanted to start checking the concrete. The basic idea is you're sending ultrasound through. How long does it take? You have to have access to both sides. And you can find flaws and voids and honeycomb, and like I was using, the basic principle was ultrasonic pulse velocity, but tomographically analyzed to produce those images in that research I showed you. Factors that affect it: aggregate type, content, moisture content, presence of rebar. Not a big effect unless you're going right on a rebar. But this is an early meter. It's the V meter. The first one was probably the Pundit from England, and then James put out a V meter. But it's basically, it would read a time. That's all you'd get. It'd say it took X time, and you have a calibration bar. And that's okay for the laboratory, but if you're doing forensic work, you'd rather have a unit that maybe has a screen. Simple metal detection. That was pretty much what was used to find rebar for a long time, until the early radar, or of course X-ray. But the early radar that Peter showed, we've used some of those paper units too, and that's it. It's a little bit like the Polaroid photographs I mentioned. When you had a paper trace, you didn't process it anymore. That was what you got. So the digital processing is a key factor, like you all know. Being able to take data and digitally process it is a huge factor in improving our accuracy. I've got a few more things. I don't think my time is quite up. Okay. How come I can't get to that? Who knows 2007? Maybe it's opening. Okay. What I wanted to show you was some of the other imaging type things that are now being done, if I ever get it to come open. All right. I think I should close this one. Maybe not. Okay, we mentioned ultrasound. Faster is better. This was an interesting calibration of ultrasonic pulse velocity on foam concrete embankment materials for the North Carolina DOT, because they had concern because laboratory cylinders didn't predict strength. Now, you may not have used foam concrete. It's basically cement, fly ash, water, and an air foaming agent, if you will, sprayed out in a garden hose. That's really more like a fireman's hose. And you place it in forms, and you can build a reasonable strength approach embankment to a bridge. And they did it in the swampy ground of North Carolina, put it on top of timber piles. But some of the lab results on this material, which actually floats, in fact, the first time they used this type of embankment, they got flooded by a hurricane and it floated away. It literally left. You've got to have this thing tied down. They now seasonally build it correctly. They try and avoid hurricane season. But they had low-strength cylinders, and so they were concerned in the field what had occurred. And so we went to the laboratory, they had a bunch of cylinders, and we did pulse velocity testing, then we crushed them, and we developed a correlation that was really quite good. You can see that strength is 0 to 350 psi on the vertical scale, and it's from 5,800 to 7,000 feet per second, about half the speed of concrete, I might add, but an excellent correlation. With this correlation, we went to the field and did surface wave testing, which looks down and shows you velocity versus depth. It was okay, the lab testing was wrong, and they actually accepted. A year later, I saw them again and said, how'd that work for you? They said, great, and the road is performing great. So you can use these technologies with proper calibration. You'll notice we have a lot of calibration there. That's a good 20 or 30 samples to have confidence in the testing. Pulse velocity, but if you don't get, just having a table of pulse velocities may not be so useful because it's the average velocity over your path. This was a case of honeycomb void, as you can kind of see on the left, in a column where the contractor didn't consolidate it, just dumped it. About half the column turned out to be okay and half was a problem. But we did tomography. And the tomography there shows the void, some gaping void. It was a good contractor with a dishonest employee that was leaving them that just didn't give a darn and just dumped it. And so it was done on a 1-foot grid north to south with ultrasound. And that was a typical good signal. Time 0 is little noise, but the strong signal's in the middle of the screen with good velocity. Now right next to this was void. And the void had almost no signal. There's a tiny little signal in there that's delayed as we looked at it. So we analyzed that tomographically to give them 32 slices horizontally. This is like 5 foot up in an area of visible void. Part of that area was good, just by chance, but a lot of it was void and poor. And about half the column was void and poor, and they had to tear it out. But a case where in one day of field testing, we could really image the situation, give them these shots, they could decide what to do with it, and they correctly decided, I think, that they couldn't repair it, with 16 of 32 slices to a 32-foot tall column being bad. And the picture is worth 1,000 words. Just like in medicine, I think we have to move towards imaging as we present data. Peter touched on this, whether it's a true image like this is or just showing the results in an image, a technical image, if you will. It helps a lot to visualize it. Applications of impact echo, finding void, thickness, quality assurance. Gauges are getting small. This is a concrete thickness gauge we make. It's quite small, handheld, technician friendly. And it's not big at all. It goes tap, 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 and showing an echo, 6 inches, right there on screen. Trying not to show them frequency. That 6-inch echo, I know, is 12,000 hertz. You don't want to know that. You want to know it's a 6-inch echo. We have to get clearer in our presentation of data. And that's the physics of impact echo. Just velocity equals, well, the depth is velocity over twice the frequency. I conceived an idea of scanning. And I was sitting on an airplane. In fact, Harold, are you in the room? Okay, the gentleman I worked with from, yes, you are. Sorry. But it was your project. I was sitting on an airplane after doing ultrasonic pulse velocity testing on a 3-inch grid all day at the Kansas City airport. And son of a gun, the idea came to me, maybe we should scan. So, and try and get away from point-by-point testing. We still do a lot of point-by-point. But that rolls and taps. And we've been using this with our PC that we used over at Point de Hoc with Tanya's students to roll and scan. And so you've got void in post-tension bridges. And as we come along, there's the simulated void being put in. Restruction Corporation grouted these for us. We had different sizes of voids. We did the scanning vertically across it. And a duct that's not grouted, which is a corrosion risk, shows up as a void, and it looks thicker because the resonant frequency drops because it's not as stiff. And so that's what happens. It's like it's got a hole in it. And that's the shift in frequency peaks from an empty duct versus grouted. We scan across it, testing every inch, going tap, tap, tap. You get color plots. The color plots in this case, those are the 4 ducts side by side. The red and the white are thicker and voided. And it correlated quite well in this National Cooperative Highway Research Program research. You look at it in 3D sense. That's the skewed data view. To just grab it and look at it, and where it pops up to the red and the white, that's thicker along those 4 ducts. And so it's being applied in the real world. This is a project in England. Big bridge over there, the Orwell Bridge over the Orwell River. And that's just on the inside with the PC, and there's the technician that scanned up the wall. Bless him, he had a book of the 500 best pubs in England, and he took me to them. Very nice, very nice. I go back to England any day with that book. So there's our PC taking the data in the field. We processed it. Here's a good result. I should say that's 52 centimeters. Scanned up the wall, no shifts. Here's a bad result. These are voided ducts. They pop up as looking thicker as we cross them because they're not as well grouted. And that has a risk of corrosion for the strand. That's the main concern. This shows that data from 62 meters took us about an hour to get that data in the field. That's like 40 scans up the wall about every 1.5 meters. And you can even see in this where there's some evidence. The wall thickness varied of this big bridge. But this is some of the voiding right there. You can see that where it pops up. And this is some of the voiding as well, where it shows in the red and the black. Slab impulse response certainly can be done. It's an development from foundations to find stiffness and changes. Alan Davis, formerly at CTL, kind of led the way of introducing this method in the United States. Alan Davis, if you know him, is formerly, because unfortunately he passed away a few years ago. But he did an awful lot in non-destructive evaluation. Surface waves. Mentioned surface waves briefly. This was a project that got an award from ICRI in 1995. Acres International and was working with us to look at condition assessment of this dam, and then they recommended repairs. And that's an old dam in Michigan with a log chute in the middle. That's what that feature is. The problem was the shotcrete was coming off. They'd put it on too much freeze-thaw damaged concrete. They didn't remove it well. So after 3 years, the shotcrete was coming off. And we did impact deco, but it was so debonded that didn't work so well. Surface waves worked much better, where we had 2 receivers and hit it with a hammer. It's got more energy in the test. And we could see that our goal was to find the good concrete behind the front concrete. So we did that kind of testing, went tap, 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 thicker hammers. We got this kind of result, which shows, technically it's probably a little too technical, but it was fast shotcrete over freeze-thaw damaged concrete over better, deeper concrete. So we mapped out that it was about plus or minus 6 inches to 18 inches deep of freeze-thaw damaged concrete. They said, great, we can remove that. When they excavated it, correlated very well. They could save the dam without re-permitting it, which would have been a problem otherwise. So, and that just shows the surface wave unit even being done in the gauge and the velocity of that. The galvapulse, I mentioned that earlier, very similar for getting corrosion rate, concrete resistance tests, and then you can plot it up in 2D fashions of the half-cell potentials, or 3D, this is a 3D presentation, on a grid from a deck, half-cell potential, the corrosion rate, and the concrete resistance. So we're getting more and more imaging. There's certainly infrared thermography, taking pictures and looking at heat differences. This is a very unusual study to look through a traffic membrane and try and find, could we see little defects? They were small, tiny blisters, so a very sensitive study. And it actually worked, but we could only see 3-inch and larger blisters under the urethane traffic membrane, because that really masks the fact of heat change over a blister. It heats up faster and cools down faster than solid concrete. And that's what we found, and the pictures show that. Right here, as time went by, the sun heated it up, and it was best around 9 o'clock, those 2 little blisters. So I think this has been published previously of using various things for this. The one thing I wanted to show you in closing, if I can escape out of this. Well, I may not show it to you in closing. Maybe I have to close. I got about 1 minute. What I was going to show you is just a radar image that is now being done with 2D and 3D radar. It literally starts to look like an X-ray. You can scan it and you can see vertical and horizontal rebar and actually look inside the structure to show that. But I sure appreciate the time today, and if you had a quick question, I'd be happy to answer it. Yes, sir.
Radar now, the next generation, are more reliable or accurate than ultrasound?
No.
Is there an advantage to radar overall?
There's advantages to each of the methods, and in fact, that's one of the reasons we wrote up this simple guideline as the evaluation committee that should be published sometime within the next year, to guide people towards which methods do what purpose. Radar is an excellent tool, and if you want to find metal, yes. If you want to image metal, you're not going to generally use ultrasound. But if you want to look at concrete integrity, radar is getting much better, but it's not as good as the stress wave methods, because the sonic and ultrasonic interact more with it physically. Radar can still show you things, and there's research being done to find delaminations in bridge decks, for example. And you can find certain types of anomalies. But that's one of the points I want to make about non-destructive evaluation. You don't expect your doctor to use one method to diagnose everything, right? You're going to be using a suite of methods depending on the target and the problem. And that's something to keep in mind. And that's really what I hope our guideline does for people, is to get them which methods work for which applications. That's why we worked on that. Yes, it does. And it works better in concrete for depth than radar does in that regard. And we use all those technologies. But thanks for your question. It's a good question. Any other questions? Okay. Thanks again. Have a great conference. If you want to see me, I have to tell you, I'm here today, exhibiting today, and I've got a chance to go test for our company a 600,000-pound overload in New Orleans tomorrow. I was hoping it'd be next week. It's tomorrow. I got to go. So I'll be back by Friday. Have a good conference.